Let us begin in a familiar place, integration as accumulation. It is worth repeating gently that when we integrate, we are not doing something mysterious. We are adding up many tiny contributions. Each contribution is small, and in the limit of making them smaller and smaller, the sum becomes precise. In this way, integration is a disciplined form of adding. Now, one of the commonest applications of integration is the idea of area between curves. You may already know area under a curve, at least in the sense of a graph drawn above a horizontal baseline. But between curves is just a careful extension of the same idea. Imagine two graphs drawn on the same axis. Over some interval along the horizontal direction, one curve lies above the other. At each horizontal position, there is a vertical gap between them. If you wanted the area of the region trapped between those graphs, you could do what we always do with area, slice it into thin vertical strips. Each strip has a small width, and its height is a vertical gap between the top curve and the bottom curve at that location. Then we accumulate the areas of all strips. So the mental picture is simple. For each slice, area is width times height. The width is tiny. The height is the top value minus bottom value, spoken in words as the output of the upper function at that input, minus the output of the lower function at that same input. And then we integrate that height across the interval. The integral is the long, quiet summation of all those little slice areas. Let us pause and reflect. Area between curves is not a new concept. It is the same old idea of area under a single curve, but now our baseline is not the horizontal axis. Our baseline is the lower curve. We are measuring the thickness of the region between them. Sometimes the curves cross. Then a top curve and a bottom curve may swap roles. In a more careful treatment, we would break the interval into parts where the ordering stays consistent. Conceptually, you should hear this as, whenever the shape changes its structure, we adjust our slicing strategy. We integrate piece by piece. That is not an added burden so much as a reminder that calculus is sensitive to geometry. A second classic application is volume, especially volumes formed by revolution. I will include it gently, because even if you do not love the picture, the underlying idea is still the same: slice, approximate, accumulate. Suppose you have a planar region, perhaps the area under a curve, and you rotate that region around a line, like turning a shape around an axis to form a three-dimensional solid. The resulting object has volume. How do we find it? We slice it again into thin pieces. Each slice, after rotation, becomes a simple three-dimensional shape whose volume we can approximate, perhaps a disc-like slice, perhaps a washer-like slice with a hole, depending on the region. Then we do what we always do. Each slice has a thickness, very small, and a cross-sectional area. Volume of a thin slice is cross-sectional area times thickness. And then we integrate the cross-sectional area along the interval. The integral is accumulation exactly as before. The only difference is that our height is now replaced by a cross-sectional area. It is worth repeating, integration is accumulation of tiny contributions. Area is accumulation of tiny rectangles or strips. Volume is accumulation of tiny slabs or slices. The same structure returns quietly and reliably. Another application is work, which is really just accumulation in physical clothing. Imagine a force that depends on position. If you push an object along a line and the force changes as you move, then the work done is not simply force times distance. Instead, you split the motion into tiny segments. Over each tiny segment, the force is almost constant. Work on that segment is approximately force times the tiny distance. Then you add these contributions across the path, and in the limit you obtain the integral. So work is a particularly natural example of why the integral is a limit of sums, because in real problems, the quantity you multiply by the tiny displacement is not constant. Now let us bring in a smaller but very important idea, average value, which you may think of as a mean obtained through accumulation. If you have a function over an interval, you can ask, what is the average height of this function over that interval? A steady way to think is this: if you replace the function by a constant function that had the same total accumulated area over that interval, what constant height would that be? So first, you integrate the function over the interval. That gives total accumulated amount, like total area under the graph if we keep the geometric picture. Then you divide by the length of the interval. And the result is the average value. Let us pause and restate it slowly. The average value is the constant level which, if held over the entire interval, would produce the same accumulation as the original varying function. Average value is not a pointwise concept. It is an interval concept. It is mean via accumulation, and this is a good moment to notice something that will echo later. Many definitions in calculus turn complicated variation into something stable by averaging or integrating. Integration takes change and turns it into accumulated totals. Average value takes a varying height and turns it into a single representative height. These are common ideas because they tame complexity. Now let us transition, gently, to improper integrals. The word improper can sound dramatic, but it really points to a simple fact. Sometimes the region we are trying to accumulate over is not nicely bounded, or the function we are integrating becomes unbounded. In a standard integral, we integrate over a finite interval and the function stays finite. In an improper integral, at least one of those comforting assumptions fails. There are two common ways this can happen. First, the interval may be infinite. You might want to integrate a function from some starting point all the way out to infinity. That is not something we can do directly because integration is defined on finite intervals in the basic setup. So we convert the question into a limit problem. We say, in words, integrate from the starting point to a large endpoint, and then see what happens as that endpoint moves farther and farther out without bound. If the accumulated value approaches a finite number, we say the improper integral converges. If it grows without bound, or fails to settle to a single finite value, we say it diverges. Second, the function itself may become unbounded at a point. Perhaps there is a vertical blow-up, so that near some point the function becomes arbitrarily large. Again, we do not integrate straight through that point as if nothing happened. We treat it as a limit problem. We integrate up to a point close to the singularity, and then we let that point approach the singularity. We ask whether the accumulation approaches a finite limit. So in both cases, improper integral really means the integral is defined through a limiting process. It is integration plus limits working together. Let us pause and reflect. This is consistent with everything we have already said. Integration is a limit of sums. Improper integration is a limit of integrals, and each of those integrals is itself a limit of sums. It is limit layered on limits, but conceptually the goal is stable. Measure accumulation. Now the most important conceptual question in improper integrals is convergence versus divergence. Convergence means, as you extend farther out, or as you approach the problematic point, the total accumulation settles to a finite number. Divergence means it does not settle. And what determines convergence? Often it is tail behavior, meaning what the function looks like far out in the infinite direction, or how it behaves near the blow-up point. There is a soothing lesson here. You rarely need to know the entire function in perfect detail. For convergence, you often need only a comparison with a simpler function whose behavior you already understand. This is an early hint of what we will later do with series tests. The exact details are less important than the long-run decay or the short-range blow-up rate. So when we speak about tail behavior, we are asking, does a function decrease fast enough as we move outward, so that the remaining area beyond a large point becomes small enough to sum to a finite total? Or, near a singularity, does the function blow up mildly enough that area under the spike remains finite? It is worth repeating, in improper integrals, the integral becomes a limit question. You do not integrate to infinity directly. You integrate to a moving point, and then take a limit. You do not integrate to an infinite spike directly. You integrate up to a point near it, and then take a limit. And you do not decide convergence by wishful thinking. You decide it by analyzing what happens as you move toward the difficult part. That is the essence. Now we shift slowly into sequences and series. This shift is not abrupt. In fact, it is deeply connected to what we have just said. An improper integral is a limit of integrals. A series is a limit of partial sums. Both are about infinite processes and whether they settle down. A sequence is a list of numbers arranged in order, first, second, third, and so on. We think of the index as a discrete step. In calculus, we are used to letting a variable move continuously. A sequence is the discrete counterpart. It moves in jumps of one step at a time. When we study a sequence, the main question is often, does it have a limit? In other words, as you go farther along the list, do the numbers settle closer and closer to some fixed number? Let us say it again. The limit of a sequence is a number that the sequence approaches as the index grows without bound. If the terms stabilize near a value, the sequence converges to that value. If they do not stabilize, it diverges. Now, a series is built from a sequence, but it is a different object. A series is not the list of terms themselves. A series is the sum of those terms, in the sense of an infinite sum defined through limits. And again, we see the same structure. You cannot literally add infinitely many numbers one after another and finish. So you define the series as the limit of partial sums. A partial sum is what you get when you add the first term, then the first two terms, then the first three terms, and so on. This generates a new sequence, the sequence of partial sums. If that new sequence has a finite limit, then we say the series converges, and the limit is the value of the series. If the partial sums do not settle to a finite limit, the series diverges. It is worth repeating because it is so central. A series converges if and only if its partial sums converge. Now, the prototype example is the geometric series. This is the series where each term is a fixed fraction of the previous one. You start with a number, then you multiply by the same factor each time to get the next term. The key behavior depends on whether that factor shrinks the terms in magnitude. If the factor has magnitude less than 1, then the terms decrease towards 0 rapidly, and the partial sums approach a finite limit. If the factor has magnitude at least 1, then the terms do not shrink in the needed way, and the partial sums do not settle. Let us pause and restate in plain words, the geometric series is the simplest laboratory for understanding infinite sums. It shows us that an infinite process can produce a finite result, but only when the contributions become small fast enough. And there is another fundamental point: for any series to converge, the terms themselves must go to 0. If individual terms do not approach 0, then the partial sums cannot stabilize, because you keep adding a noticeable amount forever. This is necessary, but not sufficient. The terms going to 0 is required, but it does not guarantee convergence. There are series whose terms go to 0 but still accumulate too much overall. So the sequence of terms approaching 0 is like a basic sanity check. Then we need sharper tools to decide whether the sum settles to a finite value. Now we move into series tests and then into power series approximations, which bring us back to calculus in a very intimate way. They let us approximate functions using polynomials, locally, with controlled error intuition. First, series tests. A test is a diagnostic. It does not create convergence, it detects it. One of the commonest tests to understand is the comparison test. The idea is compare your series to another series whose behavior you already know. If your terms are always smaller than the terms of a known convergent series, then your series converges too. If your terms are always larger than the terms of a known divergent series, then your series diverges too. This is closely related to what we said about improper integrals. Tail behavior is often what matters, and comparison to a simpler known example is a standard way to proceed. Then there is the ratio test. This test looks at how each term compares to the previous term for large indices. If, eventually, the ratio of consecutive terms has magnitude less than 1 by a fixed margin, then the terms shrink quickly enough to force convergence. If the ratio tends to something greater than 1, the terms do not shrink and the series diverges. If the ratio tends to exactly 1, the test does not decide and we need another method. Closely related is the root test, which looks at the long-term growth or decay rate of the terms by examining the magnitude of the term at index n, but spread out over n steps. If the effective per step factor is less than 1, the series converges. If greater than 1, it diverges, and if equal to 1, again the test is inconclusive. There is also the alternating test, which applies when the series terms alternate in sign, positive then negative then positive then negative, and when the magnitudes of the terms decrease steadily towards 0. In that case, the partial sums often settle, because the additions and subtractions begin to cancel more and more precisely, and the remaining oscillation shrinks. The series converges, though the convergence may be slower and more delicate. Let us pause and reflect, and gently summarize. Comparison methods ask, can we bound the series by series we understand? Ratio and root methods ask, do the terms shrink at an exponential-like rate? Alternating methods ask, do cancellations stabilize the sum when magnitudes decrease to 0? And now, from these diagnostics, we transition naturally to power series. A power series is a series whose terms are built from powers of the input variable scaled by coefficients. You can think of it as an infinite polynomial, a polynomial with endlessly many terms, but arranged in increasing powers. The key question for a power series is, for which input values does it converge? Because unlike a simple numerical series, a power series depends on where you evaluate it. Often, a power series converges within some interval around a center point and diverges outside that interval. The distance from the center to the boundary of convergence is called the radius of convergence. In words, it is how far you can move away from the center before the infinite polynomial stops behaving like a finite number. Within that radius, the power series defines a legitimate function. Outside it, the series does not converge, so it does not define a finite value. The ratio test is especially useful here, because it naturally compares consecutive terms, and in a power series the ratio often simplifies into something involving the magnitude of the input. So, in practice, we often find a radius of convergence and then we check the endpoints separately, because endpoints can behave differently than the interior points. Now, why do we care about power series? One reason is approximation. A central idea in calculus is that complicated functions can be approximated locally by simpler ones. The simplest local models are linear, the tangent line approximation. Then come quadratic and higher degree polynomial approximations. When we push this process further, we arrive at Taylor polynomials, which approximate a function near a chosen point using information about its derivatives at that point. Since we are speaking without formulas, let us describe it conceptually. A Taylor polynomial is built so that, at the chosen center point, it matches the function's value, and also matches the function's slope, and also matches the function's curvature, and so on, up to some chosen order. The more matching conditions you impose, the higher the degree of the polynomial. And the soothing intuition is this: near the center point, a smooth function behaves like its Taylor polynomial, because the polynomial has been constructed to imitate the function's local behavior to a high degree of fidelity. But we must also keep a calm awareness of error. Approximation is never perfect unless you include infinitely many terms and the series truly converges to the function. So we speak about the error as the difference between the true function value and the polynomial approximation. The error tends to be small when you stay close to the center point and when the function is well behaved in that region. The error also tends to shrink as you increase the degree of the Taylor polynomial, at least within the radius where the underlying Taylor series converges. Let us pause and repeat the key picture. A Taylor polynomial is a local model. It captures how the function looks near a point. The Taylor series is the infinite extension. If it converges to the function, it provides a powerful representation. The radius of convergence tells you whether this infinite representation actually makes sense. An error intuition tells you why near the center is the safe zone. There is a deep unity here with integration and accumulation. In integration, we approximate an area or total by summing small pieces. In Taylor approximation, we approximate a function value by summing polynomial-like contributions derived from local behavior. In both cases, the infinite or limiting process is tamed by understanding how the pieces behave as they get smaller or as we take more of them. Let us end by gathering the threads quietly. We began with applications of integration, reminding ourselves that integration is accumulation, a patient summing of tiny contributions. We used that idea for area between curves, where we add thin strips whose heights are the gaps between two graphs. We extended the same idea to volume, where we add thin slices whose cross-sectional areas determine the contribution to volume. We saw work as another version of accumulation, where varying force over distance requires slicing and summing. And we described average value as a mean obtained through accumulation, the constant level producing the same total as the varying function. Then we moved to improper integrals, and we repeated the essential point. When the interval is infinite or the function becomes unbounded, we define the integral through limits. Convergence becomes the question, and tail behavior becomes the intuition. What matters is how the function behaves far out or near the problematic point. From there, we entered sequences and series. Sequences are discrete lists with limits, and series are infinite sums defined as limits of partial sums. The geometric series served as the prototype, showing that infinite processes can yield finite totals when terms shrink appropriately. We repeated a necessary condition for a series to converge: its terms must approach zero, though that alone is not enough. Finally, we discussed series tests as diagnostic tools: comparison, ratio, root, and alternating tests, each offering a way to read convergence from long-term behavior. And we moved into power series, where convergence depends on the input value, often within a radius around a center point. Taylor polynomials and Taylor series emerged as local models and, when convergence is kind, as powerful representations of functions, with their intuition guiding how far and how confidently we approximate. And so the unifying theme, worth repeating one last time, is that calculus is the art of controlled limiting process. We add infinitely many tiny pieces by taking limits. We extend integration to difficult cases by taking limits. We define infinite sums by taking limits. And we approximate functions by building sums whose behavior we understand, locally and then, sometimes, globally. Let us pause and let that unity settle: accumulation, limits, convergence, approximation. Quiet ideas, returning again and again, each time in a slightly different form.